coverage of the game of the year between Yale and North Carolina.
If you're just joining us, we have witnessed an unbelievably well-fought match tonight, and it's come down to penalty kicks. Peterson for Yale, taking the first approach.
Oh! Spectacular! North Carolina's goalkeeper Richards just let one in past him now, so now the burden rests on Yale's Scott Sterling.
Here he comes, nerves of steel, that man, dealing with more pressure now than a submarine.
Indeed.
Oh, crowd showing some appreciation.
Johnson places the ball on the spot, getting ready. That man literally has a cannon for a leg.
Yes, he does.
Here he goes, winding up for the shot, and... oh! The cannon has fired and hit Sterling directly to the face.
We clocked that at a stunning 116 kilometers per hour.
Now that's a lot of miles per hour.
Little chance that man's nose is not broken right now.
Oh, indeed. Now Sterling getting checked out for that one. Spectacular save, though, but sadly, he's not out of the woods yet.
On his feet now, a bit shaken.
But not stirred.
This crowd absolutely loves this man.
And Sterling's teammates welcome him back a hero. For now.
He yells up again for the second attempt, looking to make it 2-0.
He approaches the ball with some determination. Here he goes.
Oh, it's high and wide, way off target.
Yes, apparently he thought he was kicking a field goal.
Wrong kind of football, I'd say.
Good show.
Back now to Scott Sterling. He looks a bit worse for wear, but ready for round 2.
And Shaw takes a moment. Here he goes with the approach.
Oh! Sterling with the fantastic dive. The ball flies straight through his hands and once again strikes him straight in the schnoz.
And let's see it again on the old instant replay. Oh, every excruciating detail captured in HD perfection.
Clocked at 129 kilometers per hour. Sterling does not look well.
2 wonderful saves and 2 definite concussions.
They may replace him at this point. He's done all he can.
Yes, as his trainer takes him off the field like a mustached lion dragging a gazelle through the Serengeti.
Adieu, Scott Sterling.
Adieu.
Yale now with their third PK. Richards is in the goal, bouncing like an infant girl.
The crowd holds their breath as he goes in. Here it comes. Oh, very anticlimactic.
Let's see who they got to replace
Scott Sterling is back!
He's still in the game!
Oh my! And he's taking a very odd tactic now.
Seems to be curling up to protect his face.
Not exactly a recommended technique, but here it goes. Wait, no, Lampert needs to tie his shoe. Oh, and that's why you do a double knot, kids.
Sterling still waiting for the kick to happen. He's probably wondering when... Oh! Sweet buttered crumpet! The ball drills Sterling right in the face.
That man's nose must be absolutely devastated. He's gonna look like a witch that blew her broom into her nose and then crashed into a hammer.
I hardly even care about this attempt. Let's go back to Scott Sterling!
The man!
The myth! The legend!
3 perfect blocks by Sterling and his cat-like face reflexes.
Absolutely incredible. Though I must say Sterling does not look well at all.
Well, you know football players like to add a bit of drama, don't they?
They're gonna take him out? No, wait! They brought him a chair!
Oh, a bold move by the manager! Bain sets up for the 4th attempt.
And this, frankly, is a gimme. He literally just has to kick it anywhere except where Sterling is sitting.
There is no possible way that North Carolina can mess up this shot.
Oh!
158 kilometers per hour!
This man can do no wrong!
Look at him beg for mercy when it's mercy that should be begging for him!
He has looked death in the eye and said, take your best shot! To which Death replies by punching him in the face over and over and over again.
If Yale makes this final shot, it's all over. But no! Oh, he misses, which means we're going to Scott Sterling!
His face is like a brick wall.
A brick wall that can feel pain and cries a lot.
Where's Sterling? Oh, he seems to be crawling away from the goal. What is he doing?
He's throwing away the bat. Oh! Sterling has done the impossible!
Look at that! He made it just right! What incredible instinct to crawl away from the goal like that!
And his teammates rush the field, happy as a lark as they slide in!
Alright guys, you can all thank Maggie from my Period 1 class for finding that hilarious video. Thanks Maggie, appreciate that. Alright, today we are going to finish up with our 7.3 notes, and we're going to talk about the domain of the composite functions. Okay. So yesterday we focused on finding what a composite function is, but now we're going to discuss what the domain will be for these things, okay? So take a look up here, and please refer back to this anytime if you need to. find the domain of the inside input function and identify restrictions. So all we're going to do is we're going to identify the inside's domain first. Then construct the composite function to identify the domain of the new function. So what's created, we're then going to look again at it and say, okay, what's hindering this? If there are restrictions on the domain of the composite functions, add them to the restrictions of the original function from step 1. If there is no overlap in restrictions between the original and composite functions, use the more restrictive domain. Okay, so you're basically looking at both situations. You're looking at the input function and then the final function, and you're saying, okay, what's hindering it? Okay, and then whatever's more restrictive, that's the one you take. So evaluate the composite function, identify the domain of each. So here we've got f of g of x. Okay, so f of g of x. Now my g of x function, just a heads up, my domain for this is negative infinity to positive infinity, because I have no x in my denominator and I have no square root. Same thing right here. Okay, x plus 1. I have no x in my denominator and I have no even powered root. So I'm putting my g of x function in. It's f of x squared minus 5. Remember, all I'm doing is I'm working inside out. Okay, this gets plugged in. Now here's my f function. Everywhere I see an x, I replace it with this junk. X squared minus 5 plus 1. I think this is actually the same thing. Okay, there's the last page. So here is my composite function for f of g of x. And my domain is, look at your original, g of x, nothing's hindering it. Look at my final one, x squared minus 4, nothing's hindering it. Boom. Okay. Same thing over here, g of f of x. This time we're starting with f of x on the inside. Again, no restrictions there. That's good news. And my g function is something squared minus 5. Okay. X squared plus 2x plus 1 minus 5. So here's my g of f of x function. Again, my domain, because I have nothing hindering it, there's no x in my denominator, there's no even powered root, boom, I'm done, right? I'm not trying to make this difficult. Alright, down a little bit, okay? Now here we have to take a little different approach. My domain for f of x is negative infinity to positive infinity. I have no x in my denominator, I have no square roots. Here I do. Here I have to say 3x is greater than or equal to 0. X is greater or equal to 0. My domain for g of x starts at 0 and it goes to infinity. We're going to use this. Alright, just quickly to go through the composite function. Your g of x is root 3x. And then this is 4 times root 3x squared minus 1. Again, I'm plugging it in for here. This becomes 4 times 3x minus 1, 12x minus 1. Okay. So this is my final f of g of x composite function. And this looks fine. But originally my input value was root 3x. This was my domain, 0 to infinity. My domain for this is negative infinity to positive infinity. What's the more restrictive one? Right here. So my domain is just 0 to infinity. You take the one that's more specific or more restrictive, if you will. Okay? F of x, plugging in 4x squared minus 1, and then this is 4x squared minus 1 squared minus 1. Let's see here, 16x to the fourth minus 8x squared plus 1. 64x to the fourth minus 32x squared. Let's see, that's plus 4 minus 1 is plus 3. Again, look at your original one. What I put in here had no restrictions, f of x. My ending has no restrictions because I have no x in my denominator and I have no root power, or even powered root. So this is just f of x, which is my domain, negative infinity to positive infinity. Okay? Alright, finally number 3, given f of x equals this. This is equivalent to 3 over x. Guys, the only thing I can't have here is 0. So it's negative infinity to 0, union 0 to infinity. Okay, so f of g of x, I'm plugging g of x into f of x. So it looks like this, 3 over x plus 1. Okay. Now, take a look what happens here. This is where we have to mix things up a bit. Alright? If you look at my new composite function, f of g of x down here, I have x plus 1 in my denominator, which means x plus 1 cannot equal 0. So check this out. My input function I can't have... Oh, I'm sorry. My apologies. I'm getting ahead of myself over here. My g of x input function has no domain restrictions. It's negative infinity to positive infinity. However, my new function, my composite function, I can't have negative 1. So my domain is just everything except for negative 1. Right? So again, input, g of x, totally cool. But my composite, I can't have this equal to 0. Boom, there it is. So for part B, g of f of x, g of 3 over x. Okay. Now I have this hindering it. Then I have 3 over x plus 2, because I'm plugging this in for g of x. This is g of x. Again, my original input function was the f of x, which I couldn't have 0. If I look at this, I can't have 0 as well. Hence, my domain is just negative infinity to 0, union 0 to infinity. Okay. So it's a lot of little checking here and there. You're checking your original function that you're inputting, and then you're checking your end composite function as well. And there it is. Okay. Lastly here, construct a response open-ended. Given that f of x equals 2x minus 9 and g of x equals x plus 3, explain how you would find the domain of the quotient function f of x divided by g of x. Well, f of x divided by g of x would be equal to 2x minus 9 on top, x plus 3 on the bottom. So looking at this, again, I know I'm sounding a total broken record here, but what do you have an x in your denominator? Yes. Do I have an even power roots? No. But because I have an x in my denominator, I have to do x plus 3 cannot equal 0. Okay? So therefore, the only thing that hinders this is negative 3. I know this is a little confusing, but with enough practice, you're literally doing the same thing every single question. Do I have an x in my denominator? Do I have even power roots? If you don't have any of those, it's negative infinity to positive infinity. Otherwise, you act accordingly. Alrighty? Good stuff. So, I wish I could remember the name of that goalie that was in that video, because I was going to be like, be like him today, and, you know, use your head. Ha! Get it? Because he used his head in the goalie saves? I don't know how I come up with these. I don't even know why I'm not a comedian right now. I miss my calling. But anyway, keep up the good work today, guys, and as always, good luck. We are all